Good day everyone. My name is Nur Fazila Alia and I'm here with my group members Aisha Liana, Nur Farah Alia and Nur Akila. Today we are presenting our case study on work, energy and power, two everyday scenarios that shows how physics shows up in real life. First, we have Farah who carries a bucket of clothes up the stairs to the lobby. Second, we have Aisha who rides a motorcycle both on flat roads and uphill. We choose these scenarios because they are things we all experience, carrying things or riding a vehicle. And they let us apply work, kinetic energy and power formulas to real situations. Our goal is to calculate how much energy and power each activity actually needs and then reflect on what that means for fuel efficiency, cost, and fairness, especially for people living in hilly areas. So, before we dive in, ask yourself, have you ever noticed a motorcycle sound harder going uphill? Why do you think that happens? And do you think people in rural hilly areas pay more to get around than people in flat cities? Let's find out together.
Hi, for our first case study, Farah is walking horizontally to the lobby as shown in the video just now. We can calculate the kinetic energy due to its motion. In this case, the mass of bucket is 8 kg. The distance Farah walking to the lobby is 20 meter and she takes 25 seconds to reach there. To calculate kinetic energy, we can use formula 1/2 mv². This calculation requires velocity. So first, we need to calculate the velocity. Distance divided by time. 20 meter divided 25 seconds and we get 0.8 meter per second. Next, substitute into the formula. And finally, we get 2.56 joule. Although Farah is holding a heavy bucket, the work done by her lifting force is actually 0 joule. Why? Because her force is directed upward, but her movement is horizontal. Since the angle is 90 degrees and the cos 90 is 0, so there is no work done by that specific force.
In this scenario, HR rides a motorcycle at a constant speed of 60 km per hour. We use the total mass of the rider and motorcycle to calculate the kinetic energy and the power required to keep moving. We use the kinetic energy formula by substituting the total mass of 160 kg and the speed of 16.67 meter per second. The motorcycle has about 22,231 joules of kinetic energy while moving. So my explanation for kinetic energy is the energy of motion. The faster the motorcycle moves, the greater the kinetic energy. We multiply the air resistance force by the speed. This gives the power required to keep the motorcycle moving at 60 km per hour. So my explanation for power is the rate of doing work. The engine needs about 2000 watts to overcome air resistance and maintain the motorcycle speed. Although motorcycles are more efficient than cars, public transportation is still the better choice for protecting the environment because it reduces fuel consumption and carbon emissions per person.
Okay, I will explain about incline plane. The scenario is HR riding a motorcycle. When riding uphill, the work done is no longer just against a resistance. It primarily involves increasing the motorcycle gravitational potential energy. Let's go, we find the work done. Total mass equal to 160 kg HR plus motorcycle. Distance along hill 200 meter. Incline angle 5, a standard road incline. Vertical height 200 times sin 5 equal to 7440 meter. And the calculation is W equal to 100 kg times 9.81 ms power 2 times 17.43 meter equal to 27358 joule. In conclusion, the work done is 27358 joule. This shows that riding uphill requires more work because the motorcycle must overcome gravity and gain weight. We calculate power required for the climb. Riding uphill requires much more power than riding on the flat road because the engine must provide enough force to counteract the weak component pulling the bike down the hill. The formula is power equal to sum F times V. For sum F equal to mg sin plus air resistance, mg sin phi equal to 100 100 times 9.81 times 0.087 equal to 136.5 Newton. Assume air resistance equal to 100 Newton. Total force equal to 263.5 Newton. Velocity 40 km per hour equal to 11.11 meter per second. Slower than flat ground due to the climb. The calculation is P equal to 263.5 Newton times 11.11 ms and we'll get 2627 watt. To sum up, the power required for the climb is approximately 2627 watt or 2.6 kilowatt. This is higher than riding on a flat road because the engine must overcome both the gravitational force action along the slope and the air resistance. As a result, more engine power is needed to maintain a speed of 14 km per hour while traveling uphill.
So, to conclude, we look at two everyday situations. Farah carrying a bucket up the stairs and Aisha riding her motorcycle both on flat ground and uphill. Using simple formulas like work equal mass times gravity times distance and power equals work over time, we showed that uphill riding demands much more power, over 2,600 watts, compared to riding on flat ground. This matters because it means people living in hilly or rural areas need more fuel and more energy just to do the same daily task as someone in a flat urban area. That raises real questions about fairness and cost. Our takeaway: understanding these energy demands can help guide better transport planning and encourage more fuel-efficient choices, especially for community in hilly terrain. In the end, this case study reminds us that physics isn't just numbers on paper, it explains real costs, real effort, and real fairness in our everyday life. Thank you so much for listening. Bye.